Hello everyone, Rugved Nakare here from torsionaltraining.com. Welcome to Module 1, Lesson 2. I'll be talking about torsional natural frequencies and resonances and mode shapes. It's a very important concept in torsional vibration. There's just no way in hell you can get through a torsional analysis without calculating torsional natural frequencies, without understanding the concept of resonance and mode shapes. So let's get started. I'm I'm trying my best to make this a very interesting and fun course. And what I've done is I found a great video on YouTube that really talks about resonance and describes the effects of resonance and describes the effects of an applied frequency that can cause resonance in a particular object. So it's a really cool video. Hope you enjoy it. See you after the video.
Jamie Vandera is famous for using the sound of his voice to destroy wine glasses. They seem to simply explode. But what's happening?
I know the sound waves broke the glass, but I couldn't see how. So I'm going to use our slow motion camera to see what we were missing. Instead of singing, I'm going to use a speaker and a tone generator. I have to find the natural vibrating frequency of the glass. I have to match this tone. That's it.
This is the exact tone to make this particular glass vibrate. When the tone is loud enough, the glass will shatter.
I can feel the glass shaking, but I can't see it. If I add a straw, then it's more obvious.
So what's happening here? The straw gets tossed side to side, but I can't see why.
Let's record it while I crank the volume. I took 10,000 frames per second, and I took 1 second. If I were to play back this whole video, it would take 8 minutes to get through.
Oh, this is amazing. What felt like the whole goblet vibrating is actually the rim bending back and forth, 337 times a second, the same rate as the sound waves. If I draw in the sound waves, you can see what's happening. One wave comes out of the speaker and pushes the side of the wine glass. The glass bounces back just when another sound wave pushes it again. If the timing or frequency of the sound waves is exactly right, the motion will build until the glass breaks.
Wow. So, as we would expect, the speaker breaks the glass nearest to it. And immediately we see a crack that goes all the way around the whole bottom of the frame. I'm going to play that back again. This is where the initial fracture happens, right nearby the speaker. And in about 3 frames, and this is 3/10,000ths of a second, we see this crack go along the bottom where the glass gets thicker and come right back up to the top where it's thin. So if we follow that a little more, this piece has just fallen off, but it doesn't in some sense even know that it's fallen off from the rest of the glass. All of the glass was shaking at about 300 hertz, 300 vibrations per second. And this piece is still doing that. You can see the corners of the glass still flexing as if they were influenced by the speaker, but the speaker is way too far away now to have that influence on this piece. It just has the leftover inertia. And we see that in all the pieces here, even along the top edge of this glass. This piece of glass is not resonant at that frequency anymore, so it can't get energy from the speaker, and all that we see shaking is the leftover energy from what the speaker gave it in order for it to break.
So, if you thought that glass couldn't bend, think again. Time warping changes the way we see the world because it makes the invisible visible.
Hi guys, welcome back. Hope you enjoyed the video. I think it's a great video, and I'll explain some of the concepts as we move forward on this presentation. The first thing that comes across is he talks about the natural frequency of the wine glass. This is a very important concept in vibrations. The one thing that every vibration analyst is chasing is to locate the natural frequency of a particular body that they're studying. Now, in shafts and in rotating machinery, the torsional natural frequency is a very important phenomenon because what happens is machine would be operating at a certain frequency and a certain speed, and if we happen to match a natural frequency in the body or in the machine, we can essentially excite the hell out of the machine and destroy the machine. So it's a big deal in rotating machinery analysis and vibration analysis. It's a very big deal. A lot of the torsional natural frequencies of a machine are found in the design stage, but even the best of the best analysts cannot always find natural frequencies, and so it's a big deal. So the torsional natural frequency is inherent to the system. It's inherent to the particular shaft you're studying, and it depends on the geometrical properties and the material properties of the particular body. And one way of thinking about torsional frequencies is, if you go up to a machine or any structure and you hit it really hard, it'll vibrate for a while and then it'll eventually settle down. And the frequencies at which this particular structure vibrates are usually the natural frequencies. So same situation in torsional systems. If you were to excite a system torsionally for a very short period of time, it'll twist back and forth at certain frequencies, and these frequencies are the natural frequencies. So why are these torsional natural frequencies such a big deal? They're a big deal because of resonance. And what I have here is a classic resonance transmissibility graph. Almost any vibration textbook always has this graph to explain the concept of resonance. And what this graph is it has transmissibility on the y-axis and the frequency ratio on the x-axis. So omega 0 here is the natural frequency, and omega A is the input frequency. And what it shows is, and transmissibility here is the response of the particular body you're studying, and response meaning the vibration um, experienced by the body. And delta here is the damping ratio. So what you're looking at is the vibration response for a particular system when you increase its natural frequency starting from zero all the way, or rather, when you increase the ratio of the natural frequency and the input frequency from zero all the way to 3 in this case, what you're trying to capture is the response of this particular system. So in situations where you have where your applied frequency is nowhere close to your natural frequency, you do not have a significant response. And in some cases, you can see a drop in response too. And as you start going higher and higher and higher, and as you start coming closer to your natural frequency, which is here, then you experience a tremendous increase in vibration and a tremendous increase in amplitude. As you can see, there's a lot of lines on this graph, and what these lines represent are the response for different damping. When you have a lot of damping in the system, then really resonance is not a problem anymore, and it tends to dampen out the big peaks. But if you have very little damping in the system, then you can excite the natural frequency tremendously, and the response is very, very big. And the one interesting thing about torsional natural frequencies of machines are that the damping ratios are very, very low. And because they're very low, it is easy to excite a torsional natural frequency and essentially shake the machine apart. Now let's jump into our next example using dierobes. We will calculate a natural frequency of a two inertia system. The two inertia systems are easy natural frequencies to calculate because the equation is rather simple, shown right here. If we have a system with more than two inertias and two springs, then it's a pretty difficult uh, system to calculate its torsion natural frequencies for. So let's get started on this. I'm going to follow the same format as I did in the first example, and I have an Excel spreadsheet uh, uploaded on the site that you can download and reference and follow the video along on how to model this two inertia system in dierobes. See you in a moment. Right, so let's get started on modeling two inertia system. So I fired up dierobes here, and we will start with a simple model and click on data editor. Of course, like we did before, we put in a description, so I'm going to call it example 2 2 inertia system calculation of torsional natural frequency. And I'll pick the units, and again I'll be using consistent English units, right? Now click on material like we did last time and click on typical steel. But we're going to do one thing different here in this particular model. We're going to set everything to 0. And the reason why we do this is because there is a modeling technique known as inertia stiffness modeling technique. And what it is when manufacturers make their rotors, not all manufacturers like to share their models with you. Manufacturers do not provide shaft drawings all the time. Some manufacturers do, but a lot of times they don't. They consider it proprietary information, and so what they do provide you is torsional information, torsional inertia information, and torsional stiffness information. So if you have these two pieces of information, you can still successfully do a torsional analysis without needing to know the full material properties and the full geometry of the system. So go ahead and set these to 0. And what I like to do is I like to name uh, these as dummy materials or dummy material. So hit save. Save it under your native folder. I example -1. All right, and then go ahead and click on shaft elements. And what we did last time is we created one element, and we will be doing exactly the same thing. So one element, sub 1, material 1, level 0, give it a random length of 10, 0, mass OD, you can give it a 0.001, 0, 0.001 dummy element. So I'll explain this here. So let me explain what I did here. So in this case, since we have no material properties, the length of this particular element, the diameter of this particular element, the stiffness diameter of this particular element does not matter anymore, because what we have here is we're going to be putting in individual inertias and individual torsional stiffnesses in this model to calculate our natural frequency. So let me show you how we go ahead and do that. So next to the shaft elements tab, there is a tab called disks. Go ahead and click this tab, and it opens up a disk data. And the way we input this is we are shooting for polar inertia. Now there's several other options on this particular tab, and a lot of these options are specific to particular parameters used in rotor dynamics. Since our focus is primarily on torsional vibration, we do deal exclusively only with polar inertia and ignore most of what else is here. So under the type of disk, you enter rigid, and there's a option of entering a flexible disk, which is also used in rotor dynamics. So for our torsional vibration purposes, we enter rigid disks. And for station number, notice that our first station here is station number 1, and what we want is we want an inertia to be placed at this particular station. So type station number 1 here, ignore the mass, ignore the diametral inertia, and then put our polar inertia, let's call it, say, 3 pound 4 second squares inch. Ignore the skews, ignore the lengths, and say call this J1. And similarly, since we want to model a two inertia system, we're going to park a inertia, polar inertia, on station 2. So click on row number 2, rigid, station number 2, polar inertia. Let's give a value of 5, ignore, and J2. And that should be it. Hit save, hit close, and there's your inertias. You have your first inertia, which has a value of 3, and your second inertia, which has a value of 5. So now coming back to the presentation that we started with, we've have one more missing component, and that is the torsional stiffness. We've gone in and we've put in the polar inertia J1, put in polar inertia of J2. Now all we're left with is the torsional stiffness. So I'll show you how to put in a torsional spring. So going back to diarobes, click on model, click on data editor, and go over to this tab that's called torsioner slash axial. Click on it, and then there's a few options here of different torsional data that you can input, and we're going to go for linear connectivity. So click on linear connectivity, and under T or A, we're going to type in T for torsional, and we want to connect a spring between station number 1 right here and station number 2. So our station I is 1, our station J is 2, and now we have the option of picking a flexible link or a rigid link. And really what the difference is, a rigid link has a very high stiffness. And in this case, we know what our stiffness value is going to be, so we pick a flexible link. So the shortcut here is F. If you type F, it just populates flexible link for you. And let's pick a value of, say, 1 e to the 6th inch pound per radian. We have no damping, so leave that at 0 and call this K1. Hit save, hit close, and there you go. Now we have two inertias and we have a torsional spring connecting the two. Now after I build a model, the first thing I like to do always is check the model summary to make sure that I've modeled it correctly. So go ahead and click on model and model summary, and then go to torsional vibration like we did in the earlier example. And we're looking for two things: the inertias that we put in and the torsion stiffness that we put in. So now notice in this case we have no material properties like we specified, and we have no inertia, no torsional inertia being calculated by the geometrical properties of the system. But we have our disk data, and we have our polar inertia at station number 1 set at 3, and our polar inertia at station number 2 set at 5. And then scrolling down to your equivalent rigid body properties, you have your total polar inertia, which is 8, which is 3 plus 5. And under our linear connections, we have a spring connecting station 1 and 2 with a constant of 1 e to the 6th. So our model is correct based on the model summary. We can now go ahead and calculate the torsional natural frequency of this model. And so now we come to the most important part of this lesson. Recall that we're trying to calculate the torsional natural frequency of a two inertia system with a single torsional spring connecting with the two. The formula is K1 into J1 plus J2 divided by J1, J2. And I'll show you how we do that in diagrams. So minimizing the PowerPoint again, go to analysis now, and under analysis we have three options: lateral vibration, torsional, and axial. So lateral vibration is exclusively rotordynamics. Since we're dealing with torsional vibration, go ahead and click on torsional vibration, and we have an analysis pull down menu here, and we have five options. The first option is the model summary, like we've been calculating earlier, and the second option is the natural frequencies and modes. Options 2, 3, 4, and 5 are advanced options of torsional analysis. They come under a different, um, they're used for forced response analysis. Since we're teaching a basic torsional course, we will not be uh, delving into any of these particular modules at this particular stage, but just for you to know that Dyrobes is capable of handling force response analysis and torsional vibrations as well. But for this particular purpose, go ahead and click on natural frequencies and modes, and notice that their damping effects, are they included or not? Now, since we're dealing with just calculating the natural frequencies, we're not really concerned with viscous damping or modal damping. These are all forced response properties. And similarly, the steady state response, time transient, startup transient, these are all forced response analyses. Again, not a concern as far as calculating basic natural frequencies and modes. So after clicking the analysis tab and selecting option number 1, the natural frequencies and modes, go ahead and click run. And now recall that we're using the academic version of Dyrobes. It's a demo version, so it's always going to pull this window up every time you hit run. In the full version, this doesn't come up. But go ahead and click OK. And if you happen to catch that black screen, that's how fast Dyrobes solves its natural frequency calculations. It's really fast. And now, in order to see what natural frequencies we calculated, there's a couple of ways of doing this. The first way is you click on this post processor tab here, and since we're dealing with torsional, scroll over to the natural frequencies and modes. And the first way of doing it is pulling up a text file, and the second way of pulling is pulling the natural frequency calculations are clicking the mode shape. So let's first pull out the text file. So click the text file, and it opens a similar looking text file as the model summary file. And what it does is it prints the same model summary that we had before, but it now goes in and it attaches your torsional frequency analysis. So in this case, we have two modes calculated, and the first mode is always the rigid body mode. Every frequency analysis, or what's also known as eigenvalue analysis, is always predicts the first mode to be a rigid body mode. And if you're interested in learning what rigid body modes are, I'd encourage you to step through some vibration textbooks to get a better understanding. But really, the first mode of concern, or the first natural frequency of concern, is calculated for us to be 730 radians per second. So R is radians per second. Or if we divide this by 60, because we have 60 revolutions a second, then we calculate a natural frequency of 116.23 hertz. So this is our torsional natural frequency for this two inertia system. Now the other way we check the calculated natural frequencies in Dyrobes is by closing the text file that we just had open. Click on post processor again, and go to the natural frequencies and modes tab, and go to mode shapes. And here is the torsional natural frequency calculator. And as you can see, we have the 116.23 hertz that was shown to us in the text file. And what we have here is the mode shape of this particular natural frequency. So Now what I'm going to do is I'm going to spend some time explaining to you what a mode shape is, but I wanted to get you to this point to see what a mode shape really is. And what's really cool about diagrams is that we can animate these mode shapes and see how these two inertias will vibrate with respect to each other. So let's go ahead and do that. What you do is you look for these options up here and you click on animation and hit play, and it asks you the number of frames you'd like and how many time delay in milliseconds do you want per frame. So go ahead and click OK. The standard option is pretty good, and you can see. So what you have here is your inertia number 1 and your inertia number 2 are vibrating, and they are vibrating out of phase with each other, which means that while this guy goes towards or this guy goes clockwise, this guy goes anti-clockwise. So they are out of phase. They're not vibrating in the same direction. So this is what you call a mode shape. So every torsional natural frequency always has a particular mode shape that is attached to it or that comes with it. And really what a mode shape is how the inertial elements in the body vibrate with respect to each other, what that shape looks like. So to give you an idea, let's go over to the 2D view. So Dyrups is great about having two types of views. In this case, we're looking at the 3D view, but you can click on the 2D view and see this is the 2D view. So if you were looking straight at the shaft, really what you're seeing here is that in this particular mode shape you have the inertia number 1 here uh, vibrating in one direction, while inertia number 2 is vibrating in the opposite direction. So for this particular torsional natural frequency, this is how the shape of your mode will look like. So for example, if we had this two inertia system, uh, suppose in a machine, and if the machine is operating at 116.23 hertz, then what you'll see is you will see this particular shape take place where, going back to the 2D view, where you'll see inertia number 1 will be vibrating in the clockwise direction and inertia number 2 will be vibrating in the anti-clockwise direction. That's just how it is, from to make a better argument from physics. Really what it is when your body is vibrating at its natural frequency, it's trying to dissipate energy in the most efficient way possible. And so when it dissipates energy, it dissipates energy by vibrating in a certain shape that is the most efficient for it to dissipate energy. So really that is the physics explanation of a mode shape. And we'll get into more of this detail as we build a little more complex models. But really, your mode shape gives you an idea of of how your inertias are vibrating with respect to each other, and where will your highest points of concern be on your rotor. So before we take this concept further, I'd like to do a quick hand calculation comparison between what Dyrop's calculated here, which is 116.23 hertz, and what a simple hand calculation of this formula yields using Excel. So let me close this animation up first, and then I'll switch over to my Excel file. And here's my Excel file. So I've just keyed in this formula here, and so we had our J1 as 3 and our J2 as 5, and we have our torsion stiffness as 1 e to the 6th, and there you go. We have 730.2 radians per second, and we have 116.23 hertz. So there you go, a hand calculation that matches perfectly with what Dyropes is predicting. And I like to show these simple hand calculations again, just for us to build our confidence in these models. So closing this out, let's take this concept a little further by modeling a three inertia system now. So let's go over here to model again, open up data editor, and I'm sure now you're developing your confidence here a little bit in modeling some of these things. So click on shaft elements, and let's add a second element now. So we'll add element number 2, keep it as sub 1, keep it as material 1. Just again at random, give it a length of 10, leave that as 0, make this 0.01 again, 0, and then stiffness OD again, 0.001, and then call this dummy element 2, right? And then again, like we did last time, we'll click on the disks tab, and we'll add a third element, a third polar inertia. So rigid, right? And then now this will be station number 3, and let's give it a inertia value of say 8, right? And let's call this J3, and close this, hit save, hit close, and there you go. Now you have 3 inertias and you have 1 torsional spring. So right away you should recognize that what we're missing is a torsional spring connecting the two. So if we don't connect this with the torsional spring, it's really not going to give us a correct answer. So we need to connect this guy, these two inertias with the torsional spring. So let's go back and click on model, data editor, and then now under torsional slash axial, open this up, and just like we did last time, click on linear connectivity and go ahead and type torsional, and this time we're trying to connect station number 2 to station number 3 again with a flexible spring, and let's give this a value of 2e to the 6th. Damping is 0 again, and call this K2. Hit OK, save, close, and there you go. Notice that the solid line that we had before has now been replaced with this dotted red line. So now we have a system with 3 inertias and 2 springs. So you will always have one more inertia than you'll have a spring. And so the number of torsional natural frequencies always depends on the number of inertias minus 1. So I'll repeat that. So the number of torsional natural frequencies calculated in any system always depend on the number of inertias in the system minus 1. So basically J, the number of J's minus 1. So let's calculate the natural frequency of this. So let's go to analysis like we did last time, click on torsional vibration, and we have the natural frequencies and modes already selected, and click run. Again, it reminds us about the academic version. Hit OK. It solves very quickly. Go to post processor, go to natural frequencies and modes, and click on mode shapes. And there you go. Now we have a system with 1, 2, and 3 inertias, and we have 2 springs. Now what's really cool about this is we now have recall that we had a 1e to the 6th torsional stiffness here, and now we have a 2e to the 6th torsional stiffness here. And so what it's showing here is that it's showing a stiffer spring by showing a slightly thicker connection here. What it's trying to show us here is a thicker spring. So go to animate again, and hit play, hit OK. And so here is your first torsional mode shape. And again, what you notice here is you have inertia number 1 rotating in clockwise, and inertia number 2 rotating anti-clockwise. So it's sort of similar to the first mode that we had. Although notice that we're almost half in terms of frequency calculated as the 2 inertia model. But the mode shape is about the same. And if you go to the 2D view, you'll get an even better idea. Notice that this guy is out of phase with that guy, and the inflection point is somewhere where it kind of was last time. But now, going back to 3D view, Now we can toggle between the first two mode shapes. So let's click on mode and click on increment. And now this is the second mode shape. So since we have three inertias, we will always have 3 minus 1 mode shapes. So now look at this mode shape. Now we have inertia number 1 that is out of phase with inertia number 2, which is and inertia number 1 is now in phase almost with inertia number 3. So let's so before we go any further, there's one setting that I'd like for us to select in this post processor window so that I can show you these inertia numbers a little better. So go to options, click on settings, and then under settings click on check the station number box and hit OK. So now you have the station numbers just like we modeled, number 1, 2, and 3. So coming back to this mode shape, now you see that you have a relative twist between inertia number 1 and inertia number 2, and then again a relative twist between 2 and 3. In 2D view, this makes it even more obvious. So look at that. So now you got this inertia number 2 that is out of phase with inertia number 1. So that's the end of lesson 2 of module number 1. The aim here was to show you two things, or rather three things. One was what an inertia stiffness model is and how to do an inertia stiffness model. Secondly, what a torsional natural frequency is, and two, what is the corresponding mode shape of a torsional natural frequency. So I'll see you now in the next module. We're done with module number 1. Module number 2 will get into more detail on inertia stiffness modeling. See you in the next module. Take care.